Okay, well, now that we've reached 4 p.m., we're going to go ahead and get started. I'd like to thank everyone who logged in so far today and joining us for this webinar. I'm just going to give you a brief sort of explanation of the webinar series and then some tips and hints for how to participate, and then we'll get started with our guest expert for today. So my name is Melissa, and I work at the National Office for the National Ocean Sciences Bowl. I'm sure most of you know that it's a high school academic competition. It's all centered around ocean science. And while we do a lot for the students every year, this webinar series is specifically for our coaches. It's a way to help them learn about our topic, our theme for each year, and provide them some information that they can take back to their teams or incorporate into any coursework or curriculum that they're doing in the classroom. So this year, our theme is Blue Energy, powering the planet with our ocean. We've chosen this theme because our finals competition is going to be in Corvallis, Oregon, hosted by Oregon State University. And the university not only is located in a prime area along the coast, west coast of the United States, for looking into marine renewable energy, but the university itself does a lot of research on the topic. So we're glad that you all joined us today. Basically, the way the webinars run is we give up to an hour for the presentation by our guest expert, and then at the end we'll have 30 minutes for question and answers. So just so you know, right now we have you all on mute as participants. So what you're going to want to do is, as you come up with questions while the presenter is going through her slides, feel free to type in the questions. At the end of her presentation, we'll go through as many of those questions as we can get to in a half-hour period. What you see right now on your screen, you can minimize the participants and the chat box if you so wish, so you can see it full screen. And then, like I said, hopefully you will write in your questions either during the presentation or just after. And please also feel free to use the little chat box, to let us know what you liked about the webinar, or feel free to email us at nosb@oceanleadership.org. The more information we have about how these webinars are helpful to coaches and other educators, the better we can find funding to host them. Okay, so today I'm going to introduce our guest speaker. It's Dr. Sarah Henkel, and she is from the Hatfield Marine Science Center at Oregon State University. And today she's going to be talking about evaluating the environmental effects of offshore renewable energy. So we want to thank her for joining us today, and I'm going to turn it over to you now, Sarah.
Thank you, Melissa. Melissa, can you give me a brief recap of who they've heard from so far regarding this topic and who's coming up after me?
Sure. You are actually our first speaker in this series. Tomorrow we're going to have a representative from Columbia Power, speaking mostly just on wave energy. That's the research he's in. And then we have Katie from Oregon Sea Grant sort of speaking more on Thursday about all the different stakeholders that have to be involved when you consider actually putting one of these marine renewable energy projects out in the ocean.
Okay. All right. Well, good. I've got a little what I call my primer of renewable energy before we get into looking at the effects, since the topic is on blue energy broadly and not just what we're doing here in Oregon. So in terms of ocean renewables, what we consider ocean renewables would be offshore wind, tidal energy, current energy, OTEC, which stands for Ocean Thermal Energy Conversion, and wave. And I'm just going to today talk about offshore wind, tidal energy, and wave energy. Marine current energy, the approach is very similar to that as tidal, just currents are moving in one direction all the time, most of the time, and tides go back and forth. But in terms of what kinds of devices you would put in, they're very similar design. And then ocean thermal energy conversion is so different, that should be its own topic. So we're going to focus on three today. I'm going to start with offshore wind because it's in some sense the easiest to wrap your head around because it's not very different from terrestrial wind, onshore wind. The turbines are very similar. But the reason we're really interested in pursuing offshore wind energy is that many of the land-based wind sites are not close to coastal load centers. I'm sure your team is well aware that most of our population is near the coast, whereas some of the really great land-based wind resources are in wide open spaces where there's not that very many people. And so if we can get offshore wind and get the source close to the load, we can save a lot in transmission and don't have to store it. There's also a lot of offshore wind already installed in shallow waters off the coast of Europe. And when I say shallow, I mean less than 30 meters, so less than 100 feet deep. And in shallow waters is one of the first places to install offshore wind because it is very similar to terrestrial wind, because basically you can drive a monopile, a pole, into the seabed in the same way that you would do it into the land, and then you've got your three-bladed turbine on top. Denmark and the United Kingdom have installed the largest offshore wind facilities, and worldwide, proposed offshore wind projects through 2010, that was the old data, equal more than 11,000 megawatts. But there's only 1,000 of that in North America, 500 megawatts each in the US and Canada. And the remainder is in Europe and Asia. So this is a resource that other countries are definitely already taking advantage of, and we're just in the beginning stages. On the West Coast, we're going to be faced with some different challenges. Most of the wind resources in the US and on the west coast of the US, and here the continental shelf drops off really rapidly. And so the water is much deeper, and we can't use these same models of turbines that are like the terrestrial ones, excuse me, because there's so much of the water column before we get to the seabed. And so you can see in this figure here, an onshore wind turbine and a shallow water turbine are very similar. At transitional depths, you could still drive a monopile into the ground, but with some guide wires on. But there's not a lot of opportunity for that. And on the West Coast, we're really pursuing deep water wind, which would be some sort of floating platform with a turbine on top and then mooring lines down to some sort of anchors. We do finally have offshore wind in the United States. This news article is from 2010. Which says, approved, Cape Wind gets the green light. And here's just a long series of bullet points showing that the project was first proposed in 2001. It was granted the first lease 10 years later. That's what that news article was about. They had a number of operational hurdles, even after getting the lease, in addition to legal challenges. And the turbines did not go in the water until 2016. And so I just wanted to orient the group to the fact that this is a very long and arduous process. There were some thoughts about rushing into renewable energy, and I can assure anyone that it's not really possible to rush into this endeavor. But these are the wind turbines that are off Block Island. A colleague of mine took this picture, and so it's very exciting that after 15 years, this project really did come to fruition. On the West Coast, where are we? We had two projects proposed. Both of them got fairly far down the funding and permitting track, but neither of them have been realized as of yet. But Windfloat Pacific was a pilot project of 5 turbines off Oregon, which was intended to demonstrate the potential of floating wind turbines. And these would be in 450 meters of water. There's also currently a project proposed off of Morro Bay, California, which would consist of approximately 100 turbines floating in 700 meters of water. So this is a very different approach than what we've got on the East Coast in Europe. Okay, so that's the end that I've got for wind, because now we're going to switch gears and talk about marine hydrokinetics. But as we go through the environmental effects later on in this presentation, in terms of marine environmental effects, I want the viewers to realize that when you're talking about a platform like this, where you've got mooring lines down to an anchor, the environmental effects that we would consider for this type of installation will be very similar to those that we would talk about any sort of wave energy device, where you've got a floating component and mooring lines down to anchors, because it's really the structure that is the element that has the most effect. And of course, when you're talking about a wind turbine like this, you're not going to experience many marine effects of the turbine. Okay, so now switching gears to marine hydrokinetic ocean renewables. And these are the types of renewables where you're gaining the energy by the movement of the water. And so that's why it's the hydrokinetic, and this is why wind does not fall into this category, because in that case, the wind is generating the energy, not the water. So we're going to talk mostly about tidal and wave, but as I mentioned, marine current technologies would fall into this category as well. So why marine hydrokinetics? Well, the ocean is the largest, most concentrated source of renewable energy on Earth. And we estimate that it has the potential to supply about 10% of the world's energy needs. Water is 1,000 times more dense than air, and so you can get a lot more power from moving water than you can get in moving air. It is always available. Its strength may vary, the tidal strength may vary, and the wind or wave energy may vary, but there is always a minimum amount of energy moving through the system and thus able to generate. It's got really great predictability. You can pull up a tide table for years, decades into the future, and so you can predict roughly the amount of energy you could get from a tidal system quite a ways out. For waves, we've got extremely good predictability of the wave energy with about a 48-hour window. So we've got some really far offshore wave energy measuring buoys that can accurately predict the nearshore wave energy with about a 48-hour lead time. So that's very helpful for utilities with managing their sources and their load. As I already mentioned, much of the population is near the coast, so the sources are close to the load, so you don't have to transmit the energy very far. In most cases, we believe these will have low visual impact, and of course, the real reason we're looking at all of this is there's no fuel volatility and no emissions. So tidal energy capture is not a new idea. It's been around for a long time. In this case, tidal stream systems make use of the kinetic energy of moving water to power turbines, and they might be light current turbines or wind turbines. An old technology, very old technology, were tidal barrages. And these are essentially dams across the full width of an estuary. I think I've got a picture, yeah. So what happens here is this sort of dam has gates or doors in it, and the doors are open during high tide, and the tide comes flooding in, and then they close the doors. And then on this side that you can see, the tide will go out, and then there's a lot of water built up behind this dam. And then when the tide is at its lowest point, naturally on the outside of this dam, they can open these doors, and the water will rush through over turbines and spin the turbines and generate energy. As you can imagine, altering an entire tidal system has the potential for pretty large environmental impacts. And it also basically makes this estuary unusable for navigation because it goes completely across the estuary. So that's not an approach that's been used very much. So where we are today is putting tidal turbines in the tidal flow. And so I've got just a couple of these to show you. This is one, Marine Current Technologies, and there's one deployed in Strangford Lough in Ireland, I believe. And so you can see it has 2-bladed turbines on either side, and this company has taken an approach where they can ratchet these blades up and down this monopile so that they could do maintenance on them out of the water. And this is really important in tidal energy systems because if you have to do maintenance on these with boats or scuba divers, you don't have a lot of opportunity. These are, of course, put in very high energy tidal systems. And so if you want to work on these, you need to do it during slack tide because otherwise the tide is pushing your boat or your divers in one direction or the other. And that's about a 20-minute window when the tides are changing. And so they have to come up with some innovative ways to do maintenance on these. And so this was one approach. Verdant Power is another tidal energy company, and they put some turbines in the East River in New York, and they put in, I think, 5 turbines, and they were able to power a grocery store that was also located on the East River, and they sent all the power to the grocery store. So that's a neat story. Open Hydro is another kind of tidal energy device, and you can see that this is a really different looking turbine. So the one on the left is an artist's drawing of what they think it'll eventually look like, but while they're still in the development stage, they've got this one over on the right, which is the real one, and again, they can ratchet this turbine up and down these 2 poles to do maintenance on it and make adjustments while they're testing it. And this one has some appeal because, as you can see, the potential for blade strike of an organism seems a lot lower. So now we're going to talk about wave energy capture. And this is where I spend most of my time and where Oregon State University's expertise mostly lies. These are cartoons of a number of different types of wave energy devices, and then I'll show you real devices of these different types. So the first one on the upper left is called a point absorber, and this takes energy from the up and down motion of the wave, and it could be having, it may have a piston in there, and so you've got a float moving up and down on a spar. And there could be hydraulic fluid in there generating electricity, or one that OSU developed is one that's like it's a coil with a magnet. So say the spar is a magnet and there's a coil in the float moving up and down, and you can generate electricity that way. The attenuator also takes advantage of the back and forth motion of the wave and would have some sort of hydraulic fluid or piston in that joint that you see. The one on the upper right is a submerged pressure differential, and this is something that would be found in shallower waters where the depth difference between a wave crest and a wave trough is greater relative to the entire depth of the water, so that you would actually realize a significant pressure differential of lower pressure when the trough is passing over and greater pressure when the wave crest is passing over, and that would push some sort of piston up and down. In the lower left, we have what's called an oscillating water column, and this technically is generating electricity by the movement of air across that turbine, but the water is pushing and pulling that column of air past that turbine. And so this is something you might see actually on a shoreline, although I think I've got a picture of one, an offshore one. In the middle on the bottom is what we call an overtopping device. And this is another turbine, and the water spills over the top and then turns a turbine somewhere in the middle, and then the water drains back out to the source. Finally, on the lower right is an oscillating surge converter. This would be another shallow water device because this is taking advantage of the back and forth motion of the wave. And so you would want to place this kind of device near shore in shallow enough water where the bottom of the ocean is distorting the wave, which we would normally think of as a circle of energy, so that it's more of an ellipse and more of the energy is in the back and forth portion than in the up and down portion. And so the wave energy is then pushing this flap back and forth. So here, arranged somewhat similarly to my cartoons, are some actual devices of each of these types of wave energy. And so one that we've heard from a lot in the US is Ocean Power Technologies. And this is a point absorber that moves up and down and has a piston in the middle. The one in red in the middle is an attenuating device. And this is the Pelamis wave snake. And this has been deployed multiple times off Scotland and has been deployed off of Portugal for testing. Unfortunately, this company is no longer in business. They were doing pretty well in Europe, but didn't quite make it. In the upper right is one example of a submerged pressure differential. And so these are basically balloons on top of pistons. And again, the difference in the pressure between the wave crest and the wave trough would push those balloons up and down, pushing the pistons in the bottom. The lower left is an offshore oscillating water column device that I think is fairly unattractive. It looks pretty cumbersome, but there is a turbine in the middle there, and the up and down motion of the wave forces the column of air over the turbine, and then the trough of the wave would then suck the column of air back through the turbine. Lower middle is a overtopping device called the wave dragon, and so the waves would splash over this red part, and there's turbines in the bottom of this, and as the water passes through the turbines, energy is generated. And then in the lower right are two examples of oscillating surge converters. The BioWave one in the very bottom is generating electricity at the site of the devices, and so you can see electrical cables in this drawing. The Oyster is a very interesting one and has also had pretty good success in Scotland. It was called the Oyster, as you can imagine, because half of this bivalve is fixed to the sea floor, and the part with the yellow can open and close with the oscillating waves. And what you see coming off of here is actually a high pressure water line, and the turbine is located on shore. And so a number of these devices would work in concert to push water in a closed system, so it could be fresh water, in a closed system through the turbine that's located on land. And in this case, all the electricity is generated on the land, which I can see having some major advantages in terms of maintenance, as opposed to having your electrical components in seawater. Here's an example of another submerged pressure differential that, rather than having the pistons offshore, is also turning an onshore turbine. This one is interesting. That's right, I have this picture in here because it is not a closed freshwater system. It is an open seawater system. And so in addition to generating electricity by turning the turbine, it's pushing this seawater through a desalination filter and trying to desalinate water, which is a very energetically expensive process normally, and generate electricity as well. So pretty ambitious project there. And the last example I want to talk to you about is another kind of submerged pressure differential, and this is one developed by M3 Wave Company, and this is it's called M3 because it was 3 guys named Mike, and they were all OSU students in the late 70s, early 80s, and went on and got real jobs doing other things, And when interest in renewable energy surged again, they got back together and dusted off their student project and looked to see if it would work. And their little pool-sized one still worked. And they've been working and developing this technology, and actually did do an offshore deployment a couple of years ago off Camp Rylea up near Astoria, Oregon, near the Columbia River. And so it's a very exciting story about some OSU students who have really made it to the big leagues. And the way this works is essentially there's a big bag of air in each end of the I-beam looking thing that you see here. And in the middle, in the eye part, is a bidirectional turbine. And as a wave crest passes over one end of the I-beam, there's more pressure. And so that bag gets crushed, deflated, and the air that's in that bag goes through the turbine into the bag at the other end, which is presumably under the trough and lower pressure. And then as the waveform moves over, then the bag at the other end of the I-beam has more pressure on it and compresses and sends its air back across the turbine to the other end. So pretty innovative and also a really different shape, different presence on the seafloor and in the water column than some of the other ones I've shown you. Okay, so Melissa, could we do a little mini question and answer now before I get into the environmental effects, if they've got any questions about the technology in general?
Sure. So yeah, if you have any questions about the tech that she was just talking about, go ahead and type it into the chat box. Any questions?
Okay, well, it's okay if you don't.
Okay, none have come in yet.
Okay, so I threw a lot of different styles of devices and types of devices at you, and so I wanted to take a closer look at two of these, which I think represent sort of ends of the spectrum on wave energy devices, and give you some more details about them so we could start thinking about what the potential environmental effects would be. Oh, I see a question about the expected output. So this is a good time to do that. I don't have those specs on here, but for example, the ocean power technology device at the top would put out, it's rated for 150 kilowatts. And then the oscillating surge converter, the oyster here at the bottom, they would be deployed in trios so that as they're flapping, they would be offset. So as they're flapping, there's constant pressure on the flow line. And so 3 of those would generate about 1 megawatt of energy. So you can see that you would never have one of them but deployed, but one of them you could estimate might be about 333 kilowatts. So a single oyster is a little bit more than a single ocean power technology. Now when you give the ratings, that's the maximum it's expected to generate under perfect conditions. And you can imagine that the ocean is never perfect conditions. They're not perfect wave forms like you could generate in the lab. And so no device is going to ever be operating at 100% capacity, but it's a way to compare among devices.
Okay, there was one other question that came in just saying, do the 3M I-beams have to be calibrated for typical wavelength and direction in the field? If you had the exact wavelength as the length of your I-beam, would the pressures be the same?
Yeah, so actually that was something, they did some testing in waves in the Henkel Wave Lab here at OSU, and it was surprisingly effective at a wide variety of wavelengths. So you would want to orient them in the direction of the prevailing wave energy, but of course that's going to change. The prevailing direction of waves is going to be variable, and you want to build them to the prevailing wavelengths of your deployment location. But they were, like I said, surprisingly efficient across a variety of waveforms, because there's always going to be some sort of differential, and so they're always generating some sort of energy, even if they're not perfectly tuned to the wavelengths that they're experiencing. Good questions.
Yeah, and then we'll ask one last question, then you can get into the rest of your presentation.
Sure.
Extracting energy from the ocean will reduce the energy remaining, slow currents, dampen waves, etc. Is this an issue?
So that is one of the environmental effects that need to be considered. At the most efficient device that we've been able to design in the lab, which is not something deployed, can extract about 15% of the energy from the wave. Most of them are going to generate between 5 and 10% of the, or extract between 5 and 10% of the energy of the wave that is passing by it. And the wave height goes by the half of the wave energy. And so if you reduce wave energy by 10%, you're going to reduce the wave height by 5%. And so it's fairly minimal, especially for these offshore ones. By the time the wave would get to shore, you're going to have barely measurable, if at all, effects on the wave height reaching the shore. And so it's something that at this phase is not terribly concerning, because we're at the phase of testing 1 to 5 of these devices at a time. But if this field ever gets to the point where you've got deployments of 100 or 200 devices, that's definitely something that needs to be considered. And one of the areas of research at Oregon State University is how to deploy these staggered in such a way that you're allowing spaces between them for the waveform to continue uninterrupted, and so that then they can come back together at the back side of these devices, and so that on average you're taking very little energy out of whatever the wave that ends up hitting the shoreline would be. Good. Okay, so this is a exercise I do in my classroom where I have the students get into different teams and have them, one team considers the potential environmental impacts of the point absorber, one team considers the potential socio and economic ocean user conflicts of the top one. A third team would consider the environmental impacts of the oscillating surge converter, and a fourth team would consider the potential social, economic, ocean user impacts of the oscillating surge converter. And Katie will talk to you more about the ocean user conflicts or socioeconomic impacts or opportunities of these when you hear from her. But so we'll focus on the environmental impacts. So the point absorber is going to be more of an offshore device. And so this particular one is rated for like 50 to 70 meters of water, 165 to 225 feet. It's going to be about 3 to 5 miles from the coast. The float diameter is pretty big. So what the main picture is an artist rendition, and the inset is an actual photograph of one of them. So the float is about 11 meters across, 3 meters high total, the disc, the float disc. The entire structure above the water is about 9 meters high. The draft is how far down in the water column it goes, so about 35 meters down into the water column. Then it's got, what would happen is this electrical cable that looks like it's coming out of the bottom of it would go to a subsea pod, and many of the devices would be plugged into this subsea pod to have one large cable back to the ocean. So in addition to the anchors that in this picture look like hockey pucks but are really about the size of a 2-story, 4-bedroom house, you're also going to have these 6 feet by 15 feet substation pods. So you've got, for every device, you've got 4 seafloor, smallish seafloor components, whereas with this oscillating surge converter, it's in much shallower water, much nearer shore, and it's got one giant seafloor footprint, and then takes up the entire water column, and then 2 to 4 meters above the water column. And so as we move through talking about potential environmental effects, I just want you to keep in mind that there's general environmental effects, but the different devices might have more of one versus more of the other or less of another. So in general, these are the components of the device that we consider when we're thinking about potential environmental effects. And we think of this in a stressor-receptor framework, and so this is what we would call the stressors. So as we already talked about, there is going to be some reduction in wave energy. There's also big hard parts, hard structures in the water column that weren't there before, and on the seafloor that weren't there before. There's cables in the water column. There's noise that's generated by either the device or the mooring system. There's lights on the surface of it. They're going to need to be there for safety, for boats to know that they're there. And there's going to be some generation of electromagnetic fields because most of these devices are generating electricity offshore. So what are the receptors that we think about as receiving these potential stressors? Chemicals would be, we would think about hydraulic fluid if it was the kind of device that has hydraulic fluid in it. They're also likely to be coated with anti-fouling paint, and so there could be some leaching of chemicals from the anti-fouling paint or just from concrete anchors. Okay, so we've got hard structures. So right there in the middle, we know we're certainly going to get fouling organisms. Anytime you put hard structure in the water, you're going to get formation of an artificial reef. So this is an effect that we fully expect will take place. You'll also get the attraction of rock-associated species, which is still considered the artificial reef effect. So some will grow on it, and then some will be attracted to it. The electromagnetic fields and the noise could result in changes to fish or crab behavior. Some fish are electrosensitive. Some researchers and people believe that crabs are electrosensitive. Some fish also use noise to know where reefs are, to either go to them to settle or go away from them because they're think they'll be preyed upon by reef fish. And then we also have to worry about noise for marine mammals, those that use echolocation and even those who don't. Cables could present an entanglement risk if not properly tensioned. More than the risk of entanglement via the cables themselves, there's more concern with derelict fishing gear getting caught in a cable, and then that derelict fishing gear resulting in an entanglement threat to other species. These cables are not going to be loose or looping, so so that things could get entangled in them themselves. Lighting up at the top could result in changes to bird behavior. Birds know where land is because there's light on land. If you had a large installation, say 100 of these offshore, and each one of them had a light on it, you can imagine that that could look like a coastline to a bird. So that's something to consider. And the reduction in wave energy, possibly, and certainly the presence of the anchors over here on the lower right could result in changes to sand transport and sedimentation. And then finally, we've got to consider the cumulative effects of these arrays. All of these stressors from the devices themselves, and an installation such as this would likely result in a lot more vessel traffic in an area for maintenance, that sort of thing. And so it's not just the effects of the devices in the water. One of the takeaways that I hope you get out of this, as I talk through how we consider each of these potential stressors, is the difference between what we would consider an effect and what we would consider an impact. There's no doubt that there will be effects of these installations. We define an effect as a change, and certainly if you put a hard structure in a sandy area, there are going to be effects of that. There are going to be changes to sand transport and sedimentation. There is going to be growth of fouling organisms and attraction of rock-associated species. There will be some electromagnetic fields where you generate electricity. And so really, we've got to look at this whole list of potential effects, and the research we're conducting now is to determine which of those are impacts that we need to monitor, that we need to mitigate for if these installations go forward. We can, in the US, learn a lot of lessons from other offshore energy installations. We've got a long history of oil platforms in the US, and so the effects of deploying hard structure in a sandy area, the effects of potential both small-scale and catastrophic chemical leaches have long been investigated. And in fact, these platforms also, as you can imagine, have electrical cables running out to them because they need power on those platforms. And so although the major flow of energy is in the opposite direction, for a long time we've had very large electrical cables going across the seafloor to offshore installations. We can also learn a lot from wind farms in Europe, looking at the effects of many smaller devices as opposed to large oil platforms. So one thing that we know from oil platforms is that they attract reef organisms to areas that were previously sandy habitats. No surprise there. And that the assemblage of organisms that are attracted to the platform will depend on the depth of the platform. And platforms in shallow water attract shallow water organisms. Platforms that are in deep water attract deep water organisms. So that is an effect that we are quite certain would happen with any offshore renewable energy installation. Another effect is the formation of what we call shell mounds, and this is something that's been observed under oil platforms and also around wind turbine monopiles. And so this is basically encrusting invertebrates such as mussels or barnacles or clams grow on the hard structure and either are scraped off as part of routine maintenance or die and fall off. And so you'll get litter fall around the base of these structures that is from these dead encrusting invertebrates. And so what some researchers found in Southern California was that rock crab were caught significantly more often on shell mounds than at the soft bottom sites. And so while rock crabs would usually be absent from these offshore areas because it's mostly soft sediment, where these artificial structures and the cell mounds occur, you get rock crab. And the same for sea stars. And then in Europe, they've seen similar effects, finding scavenging crabs, sea stars, and certain kinds of flatfish that are less common in other areas. You can also see from this wind turbine picture that on one side of the drawing of the turbine, the seafloor is lower, and that's because we do expect to see scour around any object that's put in a soft sandy area. Just like if you put a rock in a stream, you'll get scour around that rock. You'll get sediment buildup on one side of it and sediment winnowed away on the other side of it. And so that can change the grain size, which could matter to some of the organisms that live in the sediment. And this is a horribly low resolution slide. But in thinking about EMF, as I mentioned, I should have just written over this text. As I mentioned, there are a number of offshore oil platforms, and they have electrical cables that go out to them. So this isn't a new stressor for the ocean, but it's one that hadn't ever been studied before the questions arose about renewable energy. And so what the Bureau of Ocean Energy Management undertook was a study to look at the effects of subsea cables. And they had a wonderful opportunity because one of their oil platforms off of Santa Barbara had a cable that had failed. And so they just cut both ends off of that failed cable, which is pictured as the dotted line here, and ran a new cable out to it some years ago. And so what this provided was an excellent experimental setup where you have one live cable and one cable that doesn't have any power going through it, and so you can see what is the effect of a cable itself, just the presence of the structure on the bottom, versus what is the effect of a cable that has energy moving through it. And so what they did was they measured the strength, the spatial extent, so how far away from the cable, and the variability of electromagnetic fields along both the energized and the unenergized cable. They did a lot of ROV surveys, remotely operated vehicle surveys, and scuba surveys to see what fish and macroinvertebrates were located along these cables to determine attraction or repulsion. And one of the questions was to look at whether or not a cable should be buried. And so what they found was no significant differences in either the fish or the invertebrate communities living around energized or unenergized cables or natural habitats. So there didn't seem to be a difference in the fish or invertebrates. They found very few individuals of electrosensitive species on either the energized or unenergized cables or the natural habitats. And so there wasn't any compelling evidence that the EMF produced by the energized power cable either attracted these species or repelled them. So their densities were similar across all the surveys. And probably most significant in terms of general concerns of people regarding this is that the EMF strength approached background levels about 1 meter from the cable. And so these are very high energy cables. And 1 meter away from the cable, you couldn't detect EMF that was above background levels. And so whatever EMF is generated by the cables dissipates really quickly. And so basically what they determined was given the rapidity with which the EMF produced by the energized cables diminished and the lack of response to the EMF by fishes and invertebrates, they determined that cable burial would not appear to be necessary strictly for biological reasons. Now, when you hear from Katie, you'll find that renewable energy installations in Oregon, at least where we have our experience, do plan to bury the cables, less as an environmental measure, but more in terms of a gear conflict measure. Because if you are setting crab pots, which is a very high value fishery here in Oregon, or trolling for salmon, or even if you're doing any type of bottom trawling, which is less common here but common other places, you certainly wouldn't want to pull up a cable with your crab pot or your troll or your trawl gear. And so the industry has decided that they are willing to undergo the expense of burying their cables for the basically protection it serves them and the reduction in potential user conflict. So although they didn't find any differences in overall community between energized and unenergized cables, a lot of fishermen will tell you that a crab will not go into a crab pot that has any sort of charge on it. And so a specific question remained as to whether or not crabs would be willing to cross an energized cable to be caught. And some fishermen are concerned about this because they're afraid that if installation goes into place and there's a lot of electrical cables, that potentially whatever crabs that are living inside that installation would never cross the cables to come out and be caught in their pots. And there's no rules, but general consensus that you probably wouldn't be crabbing inside of an installation where there's multiple devices. And so again, the Bureau of Ocean Energy Management did a survey to determine if rock and Dungeness crab would cross cables and be caught in baited traps. And here is a picture of their experimental setup. And this is just a mock-up, a model with small pots. But basically there's a crab pot at either end and a corridor in the middle and an entry chamber right in the middle. And the researchers put these with the pots crossing, one pot crossed the cable, and they put crabs in the entry chamber and then watched to see which pot the crabs went into to get the bait. And so here's an actual picture of it underwater, and you can see the power cable, and there's a crab in the crab pot, and on the right you can see the corridor. And crabs crossed the cable about half the time, so about half the time they went in the baited trap that they had to cross the cable to get to, and about half the time they went in the baited trap that was in the other direction. And nearly all the time the crabs went into the current. And this is probably because they were going upstream to the direction that they could smell the bait. And so it seems that the power cable has very little, if anything, to do with their choice of which baited pot to go in. So that's my story of crabs. And so again, it doesn't seem that at the individual level the crabs are having any sort of problem with the power cable. Some species of elasmobranchs, so a dogfish and a ray, were studied in very large tanks that were put out in the ocean with a power cable running through them, and they made these very large, essentially underwater cages, and tagged a bunch of fish or rays and looked to see their distribution in these tanks with the cable on or off. And the dogfish seemed to have some clustering near the cable, but they didn't suffer any effects of that, and the rays seemed to ignore it altogether. And so, well, there's a lot of research looking at the effects of power cables on the seafloor that seems to indicate they are not barriers to species migration, and they don't serve as attractions or repulsions. Some questions remain about potential EMF that's being generated by the devices themselves, because that is a new potential effect. And so as this field moves forward, we anticipate most of the research moving in the direction of looking at what is the power coming off the actual device in the water. We pretty much feel like we've got a handle on the cable effects. So that's sort of some general observations that we can learn from other kinds of installations. But what's going on in Oregon, which is kind of the forefront of offshore wave energy? Well, as my example from the Block Island Wind Farm showed, it's a long, slow road. So back in 2009, 2010, it looked really promising. There was a lot of support from the legislature in Oregon, from the executives in Oregon. I was hired by OSU in 2009 to study the environmental effects of offshore wave energy, because it looked like it was really going to go strong. And what we've gotten so far, and this was my 8th year here at OSU, is we have a test platform that does not generate electricity. It is supposed to receive energy from a device that someone else has developed and would test off of Oregon. And so this is a picture of our device. And so what we anticipate happening is that a wave energy developer would bring their device, pictured here as just a very simple cylinder with one cable/mooring line, and that would plug into our test berth by that cable that has little red balls on it. And we would analyze the power, output, quantity, and quality of this wave energy device. So we began developing this test platform in 2010, and in 2012, we had a developer test a one-third scale device for 8 weeks. And that has been our first, last, and only test that's happened through OSU. There was also, like I mentioned, M3 did do a similarly short, about 8-week test of their device at Camp Rylea near the Columbia River. But that was another very short test, and that's back in the lab. And there are currently no wave or wind or tidal energy devices testing off the U.S. West Coast. And so we're still on this long, slow, plodding path to deploying this as a utility scale energy generating device. We have high hopes though. We've got support from the Department of Energy to develop a grid connected test site where we would have 4 power cables that are going out to pre-permitted squares in the ocean. And this is an artist's rendition of our dream, where we've got different devices testing off of Oregon, and OSU is analyzing the power output, quantity, and quality, and I'm leading the team looking at the environmental effects and potential impacts of all these devices. Now, since we've had very little structure in the water, I'm going to say that we probably have the very best baseline pre-installation time series of any project proposed, because I was hired in 2009 and began doing baseline studies in 2010 in anticipation of devices testing off of Oregon. And so for the remainder of the presentation, I'll go through and talk about the baseline studies that we've done to consider the potential effects and whether or not there'll be impacts. And so this is just an actual map of that proposed siting area. So one thing that OSU has done is studied gray whale movements off of the Oregon coast to determine their speed, distance to shore, and the bottom depth they primarily transit through to determine their potential for interaction with devices deployed off of Oregon. And so our small-scale wave energy site we call NETS is just barely outside most of the paths of the gray whales that's shown here on the right. And our south energy test site, which would be the grid-connected one, is twice as far offshore, and so certainly far out of the path of primary paths of migrating gray whales. So that is good for us. That's not to say that whales won't move through our site. They certainly will, but the bulk of them that are migrating north, and when they're migrating north, it's when they have their calves with them, are migrating very close to shore, and so inside of where we anticipate testing most of the devices. Another test that was conducted by OSU is testing an acoustic deterrent. There's some concerns that these devices will be too loud and harass the whales. There's also concerns that they might not be loud enough and the whales may not know that they're there before they're sort of in the thick of them. And so they did test the effectiveness of an acoustic deterrent device. So they moored an a device that actually made the sound of a killer whale in the gray whale migratory path, transmitted the sound during daylight hours so the observers who didn't know when the sound was on or off could track the gray whale movement. And basically they found that very few whales deviated from the trajectory. So either they weren't afraid of the orca or they knew that it was not a real orca. To look at whether or not these devices will be acoustic nuisances themselves, the first thing we need to do is figure out how noisy the environment is. And so we've deployed hydrophones, which are basically just listening devices at both our North Energy Test Site and our South Energy Test Site to determine background levels of noise. 120 decibels is considered the harassment level for marine mammals. And with no devices in the water, 10% of the observations were greater than this harassment level. And so vessel traffic and breaking surf are already louder than marine mammal harassment levels 10% of the time. The work that I've led has been looking at sedimentary species on the benthos, so collecting in-faunal invertebrates with a box core, a beam trawl for collecting fishes and larger invertebrates. And in terms of baseline observations, we found that the macrofaunal invertebrates that live in the sediment are shaped primarily by the percent sand and the depth, as you would expect. They've shown very little seasonal variability, and so this is important when considering effects because they are such a temporally stable assemblage. If you see changes after you install a device, there's a high likelihood it's due to the device. Higher. On the other hand, the fish assemblages are primarily shaped by depth, and they have extremely large fluctuations based on the seasons and also interannual differences. And so if you're looking for detecting device effects on fish assemblages, you need to make sure that you're comparing similar seasons before and after installation, or similar climatic and ocean conditions, because the fish vary greatly based on this, and there could be a big difference before and after an installation that has nothing to do with the installation. maybe El Nino or warm blob or some other oceanic effect. I've also looked at Dungeness crab to see if there's what the spatial and temporal variability in Dungeness crab is, and basically we found significant differences in terms of depth, but not significant differences in terms of latitude. So all of the latitudes we sampled were similar, but very high seasonal variability. And so in this case, if we had an installation, for example, at the PUD 60 location, and it was suddenly had a lot more crabs or less crabs than NH 60 or SBC 60 on this map. I'm looking at the far rightmost hexagons. If we did see suddenly that PUD 60 had more or less crabs, then we could potentially say, oh, there's an effect of the installation. But if we were comparing PUD 60 to PUD 40 and 60 had less crabs than 40 after an installation, that's not something that we could necessarily attribute to the device installation, because 60-meter stations always had less crabs than 40-meter stations. And so that's why we conduct these baseline studies, so we can understand how we could either attribute effects to an installation or not. We also look to see how much crabs move, to see where they're potentially moving in and out of a future installation, and they move a lot. So legal-sized male crabs travel an average of 18.6 kilometers, and the maximum recorded distance between a release and recapture location was 90 kilometers. And so there's probably little concern about crabs living in a place where a wave energy installation went in and there being no potential for them to be able to be caught outside that installation. They certainly move a lot. In the 8 weeks that we did have a device testing, we did notice some scour around the anchor. So this is an ROV picture of the corner of one of the anchors, and you can see it's a little bit undercut. And there is a bunch of broken bits of shell that seem to be accumulating there at the corner of the anchor. And so we pulled the device out, like I said, after 8 weeks, but we actually left the anchors in there for 2 years after that. So at least I had something to study, even if it was just some concrete squares. And so one of the things that we noticed is that the amount of shell hash or gravel around the anchor was significantly higher than other areas. And so what this plot shows, a three-dimensional plot, so the axis going towards the back of the screen is time. That's less important than the axis, the horizontal axis, which is the locations. And so 30 meters, 40 meters, 50 meters, and 60 meters are my reference depths. And these anchors, the northeast anchor and northwest anchor, were deployed at about 45 meters. And you can see that there is a large accumulation of this very coarse material around the northeast anchor. And so it seems that this northeast anchor, which in Oregon is the one closer to shore, there seems to be accumulating these broken shells that would normally be transported offshore, and they're building up around the anchor. And so that was actually an effect we did not expect. And so then the question is this effect an impact? And what we found was that there were no effects on the medium grain size of the sediment that was under this layer of broken shells. And so in terms of organisms that actually live inside the sediment, their sediment didn't change much. There was just a lot of broken shells on top of it. There was no effect on the diversity or the abundance of those organisms that live in the sediment, so the macrofauna. But there did seem to be some effects on the richness, and the richness is just the count of the number of species. And so this is a pretty sciencey plot for this presentation. But the purple dotted and the blue dotted lines are the collections around the anchors, and the red, olive, and teal lines are the reference locations. And you can see that around the anchors, those moving averages, those dotted lines, are much, much more variable than the reference locations. And so the richness seems to, the number of species that were around the anchors seems to fluctuate quite a bit. And so that's something that I'm continuing to look into. Despite the anchors in place, we didn't see any difference in the biomass of crangon shrimp, which is a major prey species in our area over time. And we didn't see any changes in the number of benthic fish associated with either device deployment or anchors only deployment. I'm running out of time, so I'm going to finish up with the summary. So the summary of effects. We had a greater proportion of shell hash and gravel around the anchors, which is a potential indicator of scour or other processes, but little evidence for effects and therefore impacts on the sediment median grain size or the macrofauna. But even after we removed the anchors, the seafloor conditions have not recovered. So this shell hash is still out there. At least it was in April when I went out. Overall, in terms of environmental aspects, some effects will be observed, as I mentioned a half an hour ago. However, we don't, at this point, anticipate major negative impacts. We do anticipate changes to the groups of organisms that occur in areas developed for wave energy, because we certainly anticipate this artificial reef effect. So where we had formerly only sandy organisms and flatfish, we're going to have rock-associated species. We could observe changes to species behavior, and the extent to which that results in changes to the populations is something that we'll have to keep an eye on as developments expand. And so the conclusion is that these developments should be placed in areas where we're most comfortable seeing a change. So we would want to avoid places that we have rare or particularly sensitive species. The big picture is that this is new and experimental. The potential benefits may offset other environmentally damaging sources. So whatever effects or impacts are realized, we need to put those in context of what the alternatives are. Developments of these projects may limit access to areas for harvest, which I'm sure Katie will talk to you about. And so we need to continue to develop and gather information to adequately balance the benefits versus the impacts. And with that, I will take a little break from talking and take your questions.
Okay, yeah, so here's your chance to use the chat box and type in some questions. We had one comment. I don't know if it's necessarily a question. They were saying that they thought the OSU gray whale research was fascinating. They were just wondering what they found regarding the sinuosity and the movement. Do you have any ideas about that, or to send this person to look?
Right. So Bruce Mate is the lead of the Marine Mammal Institute, but Barbara Lagerquist, Lagerquist, she has been the lead on that particular project. And we're working with them to write up the results of that because everyone is interested in it. But if you contact the Marine Mammal Institute or send Barb some questions, I'm sure she'd be happy for someone's interest.
Okay. Any other questions? We'll give everybody a minute to start typing. Sure. Okay, while we're waiting, there was a question earlier about whether this would be a resource available to the students. Yeah, just so you know, we are recording this webinar, and tomorrow morning I will get it up on the NOSB's YouTube channel. So it's just the NOSB on YouTube, but we'll also have links on our website as well. Okay, a question came in. What do you believe is the economic feasibility of wave power energy as it stands right now?
Oh, you're going to ask the biologist about economics. So I can tell you that in my experience so far, the economic viability is pretty tied closely to the price of oil. So when oil has been expensive, there's been a lot more investment in renewables. When oil prices dropped, there was less investment in renewables. And so that's just been my personal observation. I think that one of the entries into this is going to be in places where the energy is very expensive already. And so a lot of developers are looking to Alaska, places that have a really good wave resource, so really powerful waves or tides, but remote places where right now they're flying in diesel and basically towns are running off of diesel generators. In places like that, marine renewables are definitely economically competitive. And it'll probably take development and fine-tuning of the technologies in those places before the price point comes down to where they're going to be competitively priced in places where energy is cheaper.
Okay, the second question is, species richness seems to be the only real downside you mentioned. Do you think this will hold up?
Yeah, so that's an interesting one. And, you know, whether or not it's a downside still remains to be seen. It's, if I do the statistics on that, it doesn't come out any different than the reference locations, because on average, it wasn't different than the reference locations. But you could see from the plot that there was a lot more variability. And so it depends on what that variability is. If you're thinking about these organisms as food for fish or larger animals, then it might be really important which species are there and which species are missing through those fluctuations. If it's species that aren't important prey items, then it might not be a significant impact. If it is species that are important prey items and they're blinking in and out, then that definitely could have impacts. And so that's a finding that needs further research for sure. And again, I would have to say that everything we've found so far has been, in terms of looking at actual organisms, just from a single deployment of a 1/3 scale device. And so I think that it's encouraging that I found very little effects of one, and so I would be wholeheartedly in favor of putting 5 or 10 out there to continue to move the technology forward and continue to look at the environmental impacts. But I don't want to, as yet, sell this as a impact-free source of energy, because certainly there will be effects that may be impacts, but we need to take this scaled approach and look at 1 and then look at 5 and then look at 10, so we can start estimating what potential impacts could be at the commercial scale.
Okay. Any other questions? We had a few people typing in, thank you. But any other questions? Okay, well, I want to thank Sarah very much for her presentation today. I want to thank you for kicking off our webinar series for this year. Just a reminder for those of you who are still on the line, you can join us tomorrow at 4 p.m. We're going to have Rence Lessman from Columbia Power. He's going to be talking about wave energy technology in particular. And that's going to be at 4 p.m. again. And then Thursday this week at 7 p.m. Eastern, we have Katie Jacobson from Oregon Sea Grant. And as you heard from Sarah's presentation, she's going to be talking sort of about the sort of social engagement, different stakeholders, and what has to be taken into consideration when we're talking about putting this type of technology in the ocean. So we hope you'll join us. And as I said, this webinar was recorded and it will be up on our website. So feel free to share it with your students or other educators. Use it however you need to in your classroom. We definitely want these webinars to be used as broadly as possible. And we thank you for sharing your time with us today. And thanks again, Sarah.
You're welcome, Melissa.
All right, well, I hope everyone has a good evening, and we hope to see you tomorrow. Good night.
Good night.
Well, thanks for participating.